All right, guys, let's go ahead and start talking a little bit more about free radical halogenation. All right, so the other day we went over some of the basic types of radicals that you might encounter, right? And we sort of alluded to the fact that some of them can have extra added stability as opposed to other ones. Sometimes that matters, sometimes it doesn't, right? So let's actually see what reactions we can do. Over the course of the chapter, there's going to be basically two general groupings of reactions that we're going to see, all right, involving a free radical halogenation. The first one is going to be halogenation of alkanes, right? That's what we did in lab the other day. While they weren't all, strictly speaking, just alkanes, they all had alkane groups on them. And basically what we did was we replaced an H with, in that case, a Br. You can also do it with a chlorine as well, right? There's a couple of different situations where you can do this, and a couple of different, basically different types of contexts that'll give you different types of products. We'll go over this. The second major grouping is going to be halogenation, excuse me, not halogenation, I have to catch myself, hydrohalogenation of carbon-carbon double bonds. And we've done this before in a way. We've done hydrohalogenation of carbon-carbon double bonds, but not free radically. And you're going to see doing it free radically gives you something a little bit different than you may accept from the ionic mechanism. All right. So initially, what our focus is going to be on number one. We're going to be looking at halogenation of alkanes. And specifically, first off, let's talk about free radical chlorination. As you might expect, chlorination, you take an alkane group, you place an H with a Cl. So how do you do it? Well, basically you take your alkane, you have Cl2, and you have to add some sort of energy source. And we did this in lab the other day. Some sort of energy source in order to promote the splitting, the even splitting of that Cl bond into radicals. Most common ways that we do it in the lab are through heat or through ultraviolet light. There's other ways you can do it too. It can be done, you can zap it with some electricity. That'll work. Sometimes sonic waves, ultrasonic waves can get it to work. But usually it's easier to do it with one of these, right? And that results in a fluorinated alkane, or an alkyl chloride, excuse me. All right. Okay, so that's really nothing too much new as opposed to what we did in lab the other day. However, one thing we haven't talked about is the mechanism. So let's go over the mechanism. The mechanism for free radical reactions, or mechanisms, I should say, are going to be a lot different than what you're used to. You guys are used to ionic mechanisms. That's where we make ions, right? Maybe you have a proton transfer that creates a positive charge. Maybe something else loses a proton, creates a negative charge. Everything's been dealing with charges, with ions. Here, we're not dealing with charges at all. We're dealing with radicals, species that have unpaired electrons. One unique feature of all these radical mechanisms is they're going to have three distinct phases. first phase is called initiation. Now, just instinctively, what do you think that's going to refer to? You hear the term initiation, what does that bring to mind? Please don't anybody say like a frat or something like that. Thank you, sir. May I have another? No. If you initiate something, you're doing what? You're starting it, right? So this is just simply how we start off. All right, to start off a free radical reaction, you got to create free radicals. You got to initiate formation of free radicals, right? In this case, this step of the mechanism looks like this. You have your Cl2, and let's just say we're adding heat, right? That heat is going to promote the splitting of that bond right down the middle. And each one of the Cl's gets an electron. Pay close attention to how I'm drawing the mechanism here, because you guys eventually are going to have to draw this. Take note of the fact I'm using these fishhook arrows with one little line on the head. That one little line coming off the head means one electron movement, like that. If I wanted to draw two electron movement, it would be a double-headed arrow. All right, so make sure that you know the difference. Right? And when all is said and done from that step, you end up with two Cl radicals. Okay. All right, second step is called propagation. And again, kind of think about the term. When you hear the term propagation, what does that mean to you? What does that imply? If you propagate something. I see a couple of people going, oh. Ooh, this is going to be like a word of the day type class too. Mixing chemistry and language skills.
It's going to be like a knock-on effect.
I'm sorry?
Like a knock-on effect.
What type of effect?
Like a knock-on effect. The initiation, the 2 CR rifles, starting more in the next one.
Sort of.
Like a chain reaction.
Yeah, chain reaction, there, yeah. When you propagate something, it basically means you continue it. You allow it to basically run unencumbered. Have you ever heard the term propagating a rumor? You spread rumors around, you're propagating. Right? So that's basically what we're doing here, right? Propagation means that we have to make forward progress in the reaction. However, we create enough species to propagate further reactions. Let me show you. All right. So let's say we had, well, let's just use methane. I'm going to draw a CH4 like that so you can see the mechanism. All right. So you have your alkane group, and you have your Cl radical. All right. The radical is going to abstract, it's going to pluck off an H radical from your carbon. And those are going to combine. And you're going to make HCl. Right? HCl is going to be a dead product. It's a dead byproduct. We call it dead because it's no longer a radical species. Right? This can't react anymore free radically. However, this other electron stays on your carbon and creates a carbon radical. Okay. All right. Now, propagation is more than one step. That CH3 radical that you just made is going to do something else. All right. Oh, let me ask you guys. Let me see if you guys can work this out. What do you think we might be adding here? What do you want to get on that carbon? You want a chlorine. Propose a way to do it.
Don't you have more radical chlorine?
So maybe this. By the way, it doesn't matter where I draw the dot. I know sometimes I'm drawing it on the side, sometimes on top. It means the same thing. So don't worry about it. So maybe you suggest doing this. Is that right?
Sure.
Good, wrong answer. It's good because, hey, we know we want to get a CH3Cl. We know that's the target product. However, it is a wrong answer because this is not a propagation reaction. When you do a propagation step, you always have to make a new reactive radical. All right, do we have any radicals in the products here? No. So that can't be a propagation. What you do is you actually react it with another molecule of Cl2. All right. The Cl2 is going to split. One of the Cl radicals will combine with the CH3 radical, and that will give you product. So there's the product of the reaction right there. But it also creates new Cl radical. And guess what that Cl radical can do? What do you think this can do? It can go looking around for another methane, right? And so this cycle continues on and on and on. In other words, it propagates. Does that make sense? Any questions so far? So yeah, this cycle basically continues on and on and on, and it keeps producing this product. All right, and then we get to the last step. That's termination. What does termination imply? What's that? Getting rid of. It's the end, right? Please tell me you guys have seen Terminator. I know it's really old and all, but man, Terminator 1 and 2 especially are like amazing. So yeah, just like the Terminator is trying to get rid of John Connor, spoilers, you're trying to get rid of radicals in this case. And there's actually a few different ways that you can terminate radical reactions. For your purposes, we're just going to go over one, and that's called coupling. Coupling, sometimes also called combination. And it's called this because all these stray radical species that are present in your reaction system, they can start pairing up to create dead species. So Matt, that reaction that you mentioned just a second ago does actually occur, right? Or that mechanism step does occur. It just doesn't occur in propagation. It occurs in termination. So this is an example of a termination. All right? This particular termination gives you product, which is kind of nice. Now, terminations don't always give you product, though. So you are going to get some waste products or side products here. Can anybody guess a side product we get out of this reaction? What's another termination that could occur? You could have two chlorine radicals that combine to make Cl2. However, Cl2 is fairly reactive, so it could go back into the cycle. What's that? You could have two CH3 radicals combined to make a molecule of ethane, right? So in this case, ethane would be a byproduct. But the major product here is going to be your chloromethane. Okay. Every one of the reactions we're going to go over in this chapter are going to have these three stages. right? So definitely a little bit different than what we've been doing, but not bad. Are there any questions so far? All right. Yeah, that was pretty simple. They can get kind of complicated. Let's say that we wanted to do this. But instead we put 2 times. What do you think that's going to mean as far as our products? How's this going to end up different than the first one?
You have less waste product?
Possibly. I'm thinking more in terms of the primary organic product.
You're gonna lose all the H's and surrounding the scale.
You're on the right track, but it's not going to go that far. Probably not. The 2 CLs on there, right? This is a dichlorination, right? Whenever you see the reaction set up, as I did it before, you can always assume that it's a monohalogenation. The only time it's not is if I put this little 2 times out there. Right? So it is possible to do more than one chlorination in an alkane. However, that can lead to some messy products. This one was pretty simple since it only had 1 carbon, right? But let's say we wanted to do this with pentane, right? Well, let's count the products. You have that. You have that. You have that. That. I want to run out of space. I think I caught them all. If I didn't, let me know. Point being, the larger point is that when you start to do dichlorinations, trichlorinations, whatever, do multiple, it tends to get really messy really fast. Okay? And that's not even taking into account stereochemistry. Oh Lord. Like this one, this would have 2 stereoisomers. This one would have 2 stereoisomers. This one. Right, so bottom line, whenever we're doing synthetic reactions, we try to avoid doing more than 1 halogenation. It's just a lot cleaner, a lot less messy. You get a lot better yield of 1 individual product, right? But it is possible to do. You can do more than 1 chlorination. Yes?
Did you get chlorines on 2 and 4?
Did I miss one? 2 and 4. Oh, yes, I did miss that one. Thank you, sir. And that one would have multiple stereoisomers. Yeah, huge, huge mess. Right, so yeah, we want to try to stick to the mono-substituted species as much as we can. Now, with chlorination though, even if you do a monochlorination, you still sometimes get mixtures of products, right? For example, if we did this I'll just use UV light this time for funsies since I haven't used it yet. There's actually two different spots where you could put chlorine. You could replace one of the H's on an end carbon, or you could replace one of them on the middle. And you do both. You get both of those products. We go back to pentane. We can get that. We get that. And we could get that. And actually, this one would exist as racemate. We'll get to stereochemistry of halogenations a little bit later in this chapter. But for now, just know that you would get a racemate. So you'd still get 4 different products here, right? Not as bad as the dichlorination, but still not really a good singular yield of anything. And if you think about it, if you're doing like a synthesis, one of those synthesis problems, like, but you're actually in the lab doing it, and you design a synthesis that has this step in it, how good's your final yield of your final product? Probably not too good, right? So for that reason, chlorination is not really as favored in the lab nearly as much as bromination. Mechanism of bromination works exactly like the mechanism of chlorination. So I'm not going to put it back on the board. Literally, you just replace Br with Cl, right? However, there's one additional feature. I'll put this one back up here. Right, we saw with propane, if we did a chlorination, we got 2 different products. Here, we only get 1. So why is that? Well, I talked about it a little bit in lab the other day, but let's go ahead and revisit. Now that you know the mechanism of halogenation, and if you need to refer back to it, just turn back in your notes. You know that at some point you're going to form a carbon radical here, right? Now, there's only 2 possibilities for this structure, right? What's one carbon radical we could form? Where could that radical species be? You tell me. On one of the ends. So that's a possibility. What's another possibility? In the middle, right? This is a pretty simple molecule, so those are the only possibilities. Obviously, we saw with pentane, you made a lot of chlorinated products, it would have more radicals. Bless you. Right? Now, these radicals do not have the same stability. What type of radical is that top one? Primary. What type is the second one? Secondary. Which one's more stable and easier to form? Secondary, yeah. So whenever you do a bromination, you always go through the most stable radical species, the easiest one to form, always. Bromination is what we call a selective reaction. It will only go through that stable radical species, or the most stable. Chlorination is a non-selective reaction process. So if you're a chemist, you're digging bromination a whole lot more than you are chlorination, because it's going to be much cleaner, much more predictable, gives you a much better yield. Why is this the case? I'll tell you in just a second. Are there any questions so far? All right. So the next logical question might be, well, why is bromination selected and chlorination non-selected? I'm going to show you. All right. To look at this, we're going to go back to energy diagrams. Remember the energy diagrams drawing the endergonic and exergonic and big hump and all that stuff? That's where the answer lies. All right. First, I'm going to draw the energy diagram for bromination. Anybody know off the top of their head whether bromination is an endergonic or exergonic reaction? I'd be super impressed if you did. You're absolutely right. You take the whole 50-50 proposition there, decided to go all in. Well, you are a big winner. Yes, bromination is an endergonic process. All right, and if you remember, that means that the energy of the products is higher than the energy of the reactants. So that's an example of an endergonic process. All right. So let's take a look at this in the context of bromination of propane. So at the very beginning of this process, we have propane, and we have that Br radical that was formed. Right? And there's a couple of different products that you could get, right? You could get, let's put it over here. You could get this product. So we'll just assign this curve right here to bromination of the very end. And we'll assign this curve bromination of that middle curve. All right. The reason we basically only make this one is because of this energy gap right there. Look at the energy of activation of each one of them. All right. The energy of activation for this process is notably smaller than this one is. That's because, I'll write a little rule here for you to remember. In endergonic reactions, PS, that stands for transition state. The transition state resembles the products. Right? Remember, the transition state is just sort of this little sort of this midway form that it sort of morphs through as you go from reactor to product. Right? In endergonic reactions, the transition state much more closely mirrors the product than it does the reactant. Since there's a notable energy gap between the two products here, that means there's a notable energy gap between the two activation energies. Okay? Y'all with me so far? This is a little abstract sometimes. If you have any questions, let me know. Bottom line, because this energy of activation is so much smaller, it goes towards this one a lot more readily. Okay? Trying to erase. Now I want to draw for chlorination. Chlorination, on the other hand, is an exergonic process. It releases energy. So you know the products are going to be lower in energy than the reactants. So there's one example of an exergonic reaction. So we can make these same assumptions here. We can say over here we have Cl radical and our alkane. Over here, we can say, I'm gonna have to adjust this back just a little bit. Over here, we can say we have one of our chlorinated products. All right. Now here's the curve for the other one. Now, what do you notice about this energy diagram versus the one for bromination? How does it differ? Specifically in terms of what's going on with that transition state. What's that?
It has higher energy.
Which one?
The transition state.
Which transition state? Well, the top one, yeah. I think I know what you're getting at, though. Basically, you see how the gap here between energy of activations is so much smaller, right? These are almost identical. That's because in exergonic reactions, the transition state more closely resembles the reactants, not the products. So that means here, the spike, the hump, to get over the activation energy for either one of these products is about the same. So that's why you can create appreciable amounts of both of them. With that endergonic bromination though, there was such a clear difference in energy of activations. This definitely was going to pick one, the lower one over the other. Okay. Does that make sense? Are there any questions about how we got there? All right. That is a good stopping place. A couple of things. Number one, change in the supplemental instruction this week. Since you guys are having an exam on Wednesday and Thursday, it makes a lot more sense to move the two SIs to Monday and Tuesday, so you can have more time to get ready before the exam. So Skylar will be in here on Tuesday, is that right? Alex will be hosting tonight. All right. What else? Quizzes. I was going to come get your quizzes, but again, we had some car issues and I didn't get here in time. Again, I'll be here until about 1:15 if you guys want to come by and pick up your quizzes. I'll be sure to put the keys up on Moodle regardless, so you can take a look at them ahead of time. Oh, a couple of you asked me about sapling and requested maybe a couple of extra days for sapling. I'm happy to do that. So I will be sure to get into sapling and extend the deadline for that. If you have any questions about your sapling homework, and I think a couple of you did, again, I'll be in my office most of the day, so just come find me. All right, that's all I got for you. Q&A session for the exam on Wednesday morning. Bring your questions if you got them. See you then.